A whale carries hundreds of times more cells than your body does. Every one of them is a lottery ticket for cancer. Multiply that by 70 years of life, and the math becomes brutal. A sperm whale should be riddled with tumors before it ever reaches old age. It should be the most cancer-prone animal in the ocean. But it isn't. Somehow, one of the largest hunters on Earth almost never dies the way its own biology says it should. And the reason isn't luck. Something inside these animals refuses to play by the rules that quietly kill the rest of us. Let's start with the part that should terrify anyone who understands how cancer actually works. Cancer is not a curse or a mystery disease. It's a numbers game. Every time a cell in your body divides, it copies about 3 billion letters of DNA. That copying is fast, and it's not perfect. Mistakes slip through. Most of those mistakes do nothing, but every so often, one lands in exactly the wrong place. A gene that controls when a cell is allowed to grow or when it's supposed to die. Get enough of those mistakes stacked in a single cell, and that cell stops following orders. It starts dividing when it shouldn't. That's cancer. It begins as a copying error in one cell out of trillions. So follow the logic. More cells means more cell divisions. More divisions means more copying. More copying means more chances for the wrong mutation to land. If cancer starts with a single broken cell, then the more cells you have, the more lottery tickets you're holding. And nobody in the ocean holds more tickets than a sperm whale. Picture the scale for a second. A human body runs on something like 30 trillion cells. A sperm whale is not twice your size or 10 times your size. A large male can push past 50 tons, hundreds of times your mass, built from hundreds of times more cells. Now imagine every one of those cells dividing over and over across a lifetime that can stretch 60, 70 years or more in the cold dark of the deep. That is an ocean of cell divisions, a near endless supply of chances for something to go wrong. By the simple math, a sperm whale should be a cancer factory. It should be almost impossible for an animal that large to live that long without its own cells turning against it. And here's where the story cracks open. They don't get cancer at anything close to the rate that math predicts. Not zero. That's the myth, and we'll deal with it honestly. But the gap between what should happen and what actually happens is so wide that it broke a piece of biology that everyone assumed was solid. Because if body size drove cancer the way the numbers say it should, then whales, elephants, anything enormous, none of them could exist. Every one of them would collapse under its own cellular odds long before it grew up. And yet, the ocean is full of giants that live for decades. So the math is missing something. Something big. This is the part that trips people up, so slow down here. You'd expect that a mouse, with its tiny handful of cells and its 2-year life, would almost never get cancer, while a whale would be drowning in it. The reality is the opposite of what the numbers promise. Small, short-lived animals like mice get cancer at strikingly high rates. Huge, long-lived animals do not spike the way their cell count says they should. A mouse and a whale end up facing cancer risks that are far closer than the raw difference in their size could ever explain. Line them up. The mouse you could hold in one hand, the whale longer than a school bus, and the one with hundreds of times more cells is not hundreds of times more doomed. It's barely more at risk at all. That contradiction has a name. Scientists call it Peto's paradox, after the researcher who first pointed at the problem and asked the obvious question nobody had a clean answer for. If cancer risk rises with the number of cells, why don't the biggest animals on the planet get wiped out by it? Why isn't size a death sentence? And notice what the paradox is really telling us. It's not just a fun fact about whales. It's a crack in how we understood cancer itself. We assumed the disease was a straightforward tax on being large. Peto's paradox says that can't be the whole story, because if it were, the largest bodies in the history of life would never have gotten off the ground. But size is only half of the trap. There's a second multiplier hiding in this, and it's the one people forget. Time. Cancer doesn't just need a lot of cells, it needs a lot of chances stacked up across a lot of years. Mutations accumulate. One broken gene usually isn't enough. It often takes several hits landing in the same cell line before a tumor forms, and those hits build up slowly over a lifetime. That's why cancer risk in humans climbs so steeply as we age. Every year is more divisions, more copying, more chances for the next bad mutation to find a cell that's already halfway broken. Now put those two multipliers together in one animal. A sperm whale has the cell count of a giant and the lifespan of a creature that refuses to die young. It should be getting hammered from both directions at once. More cells and more time, the two things cancer feeds on most. If you were designing the perfect victim for this disease, you would build something exactly like a large, old whale. And it survives anyway, routinely, for decades, hunting in the crushing dark thousands of feet down, diving over and over, its body copying its own DNA an astronomical number of times, and mostly quietly, not turning cancerous. Sit with how strange that is. We tend to think of the deep-sea whale as impressive because of its size, its dive depth, the sheer power of an animal that hunts giant squid in blackness where the pressure would flatten a submarine. But the truly unsettling thing isn't out there in the water around it. It's inside the animal. It's the fact that a body this vast and this old has somehow kept its own cells in line. Generation after generation of cells, when everything we know about the disease says it shouldn't be able to. So the scary part was never the size. The scary part is what the size should have cost, and didn't. And this is where a lot of people reach for the easy answer. They assume the whale must simply be lucky, or that being big somehow dilutes the risk, spreads it out, makes it safer. It doesn't. Being big makes it worse. Every honest look at the numbers makes the problem harder, not easier. The whale isn't escaping cancer because of some loophole in the math. The math is correct, which means the whale must be doing something the math doesn't account for. Something active, something built into the body itself. That's the real shift here. Peto's paradox isn't the answer. It's the question, sharpened to a point. It tells us that somewhere in the biology of these giants, evolution installed defenses powerful enough to override one of the most relentless statistical pressures in all of life. Not luck, not size, a solution. Cancer wasn't avoided by accident. It was suppressed on purpose, by machinery we're only beginning to understand. Because think about what that requires. For a body to grow this large and live this long, evolution couldn't just let cancer happen and hope. It had to actively out-engineer the disease. It had to build something into these animals that catches broken cells before they become tumors and catches them reliably across trillions of cells and decades of copying. Whatever that something is, it's strong enough to beat odds that should be unbeatable. And that raises the question this whole story is really about. Not why does the whale get cancer, but why doesn't it? What exactly did evolution have to change inside these animals to pull this off? What machinery is running in the dark, cell by cell, keeping a 50-ton body from destroying itself from the inside? That answer turns out to be stranger than the paradox, because the whale didn't solve this with one magic trick. It solved it with layers, and one of those layers comes with a hidden cost. Start with what the whale is not doing, because almost everyone gets this part wrong. The whale is not immune to cancer. There's no magic shield, no gene that switches the disease off, no biological wall that makes tumors impossible. If that's the picture in your head, drop it now, because the truth is more interesting than immunity. Whales can get cancer. It has been seen. The point was never that it can't happen. The point is that it happens far less often than a body this size and this old has any right to expect. And when you look at how, you don't find one miracle. You find a stack of defenses layered on top of each other, each one lowering the odds a little more. Think of it less like a wall and more like a series of checkpoints. A single broken cell has to get past every one of them to become a tumor. Miss one checkpoint, another catches it. And in an animal built to live for decades, those checkpoints have to be relentless because they're running for a very long time against a very large number of cells. The first layer is repair. When a cell copies its DNA and makes a mistake, it doesn't always just live with the error. The cell has proteins whose entire job is to patrol the freshly copied DNA, spot the mismatch, cut it out, and rebuild it correctly. This is happening in your body right now, millions of times. In a long-lived animal, the quality of that repair matters enormously, because every error you fix is a mutation that never gets the chance to stack up into cancer later. Fix more mistakes early, and you starve the disease of the raw material it needs. And here's a clue that points straight at this layer. Some of the longest-lived animals on the planet are whales. Not sperm whales specifically, in the best-studied case, but their relatives, the bowhead whale, an animal that can push past 200 years of life. In Arctic water, 2 centuries. That is an absurd amount of time for a body to keep copying its own DNA without collapsing into cancer. And when researchers went looking at bowhead biology, one of the strongest threads they found pointed toward exactly this: differences in how these animals handle DNA damage and repair. The best evidence suggests that part of the whale answer is simply a body that fixes its own genetic mistakes better and keeps fixing them decade after decade. But repair is only the first checkpoint. Some broken cells slip through anyway. So there's a second layer waiting. That layer watches the cell itself. Before a cell is allowed to divide, it passes through control points, moments where the machinery essentially stops and asks whether everything looks right. Is the DNA intact? Is anything damaged? If the answer is bad, the division gets halted. The cell isn't allowed to copy itself while it's carrying dangerous errors. This is the cell cycle checkpoint, and it's one of the oldest, most fundamental cancer defenses in complex life. A body that runs these checkpoints harder is a body that gives broken cells fewer chances to multiply. And if a cell is too damaged to fix and too dangerous to let divide, there's a third layer, the hardest one. The cell is ordered to kill itself. That's not a metaphor. Cells have a built-in self-destruct program. When the damage is severe enough, signals inside the cell trigger it to dismantle itself cleanly, on command, before it can become a problem. It's the body sacrificing one suspicious cell to protect the whole. And this is exactly the kind of defense that matters most in a giant. When you have trillions of cells, you can afford to be ruthless. You can order the deletion of anything that looks even slightly wrong, because losing a few cells costs you nothing, and keeping a dangerous one could cost you everything. This is where one of the most famous clues in the whole field comes in. And I want to be careful here, because it's not a whale. It's an elephant. Elephants face the same paradox: huge bodies, long lives, and far less cancer than the math predicts. And when scientists looked at elephant DNA, they found something striking. Humans carry a single pair of copies of one of the most important tumor-suppressing genes, the gene often described as the guardian of the genome, the one that helps trigger that self-destruct response in damaged cells. Elephants carry many extra copies of it. Where you have one guardian standing watch, the elephant has a crowd of them. Now, that's the elephant's solution, not proven to be the sperm whales. This matters, and I won't pretend otherwise. Whales and elephants are on completely different branches, and there's no reason to assume they solved the problem the same way. But the elephant tells us something crucial regardless. It proves that evolution can beat Peto's paradox by beefing up these exact defenses, More guardians, more self-destruct signals, more layers catching broken cells before they turn. It shows the kind of solution that works. And it means the whale almost certainly did something in the same spirit, through whatever route its own genome took. More checkpoints, better repair, harsher elimination of damaged cells. The details differ. The strategy, stack the defenses, trust nothing, delete anything suspicious, is the shared answer that lets giants exist at all. So now you might expect the story to end clean. Bigger animals just evolved better cancer defenses. Problem solved. But there's a catch buried in this, and it's the part that makes the whale genuinely strange instead of just impressive. These defenses have a cost. Think about what you're actually asking the body to do. Repair every mistake aggressively, halt cells at the first sign of trouble, order suspicious cells to kill themselves without hesitation. That's a body running on maximum caution, a system that would rather destroy a cell than risk keeping a dangerous one. And caution like that doesn't come free. A cell you kill is a cell you can't use. Tissue that's constantly deleting its own members, constantly halting division, is tissue that can be slower to heal, slower to replace what it loses, pushed toward wearing down over time. The same machinery that stops a cell from becoming cancer can also stop it from dividing when you actually need it to. Suppress cancer hard enough, and you can end up trading it against the body's ability to renew itself. That trade-off sits at the center of one of the deepest tensions in biology. Cancer resistance on one side, the wear and tear of aging on the other. Push too hard toward killing off damaged cells, and you can accelerate the way tissues run down. Push too far the other way, toward keeping and repairing everything, and you risk letting a dangerous cell survive. Every long-lived animal has to find some balance on that knife's edge. And a sperm whale, living for decades in brutal conditions, has clearly found a balance that works. But works doesn't mean free. It means the whale is paying a price we don't fully see, running a body tuned so tightly against cancer that other systems have to bend around it. And there's a second twist, quieter, but just as important. We keep hunting for exotic genes, dramatic solutions, extra guardians. But part of the whale's answer might be almost boring. A large animal's cells don't necessarily divide faster than a small one's. In some ways, they may divide more slowly, turn over less frantically. Fewer divisions means less copying, and less copying means fewer chances for the fatal mutation to appear in the first place. The whale might be winning partly by simply not rushing, by running its cellular machinery at a slower, steadier pace than a frantic little mouse burning through its short life. Sometimes the unglamorous explanation is the real one, sitting right next to the dramatic ones and doing just as much work. So the whale doesn't get cancer at the rate it should for the most human of reasons and the least human of reasons at once. Better repair, harder checkpoints, more ruthless deletion of bad cells, and possibly just a slower, more careful pace of life, all stacked into a single body, not one trick, a system. And that changes everything about how we should read this animal. Because if a whale can be built to out-engineer cancer this thoroughly, then cancer was never the unbeatable force we treat it as. It's a problem, and evolution has already solved it, more than once, in more than one giant, by more than one route, which raises the question that turns this from a whale story into something that suddenly involves us. If nature already cracked cancer in a 50-ton body swimming in the dark, what does that mean for the one body we actually care about? Here's the idea we have to break before we go any further, because almost everyone carries it without noticing. We treat cancer as bad luck, a random tragedy, something that just happens when enough mistakes pile up in the wrong body at the wrong time. And at the level of a single person, that's how it feels. Unfair, arbitrary, out of anyone's control. But zoom out to the scale of life itself. across millions of years and thousands of species, and a very different picture appears. Cancer isn't just random misfortune. It's a problem. A specific physical engineering problem. How to keep trillions of cells cooperating in one body without any of them going rogue. And problems can be solved. That's the reframe the whale forces on us. The moment you see cancer as a problem instead of a curse, you have to ask the obvious next question. Who else solved it? The answer is almost unsettling. Lots of animals did. And they didn't all do it the same way. This is the detail that should stop you. If beating cancer at giant size were a fluke, one lucky lineage stumbling onto one lucky gene, you'd expect to see it once. Instead, you see it again and again, in animals that aren't closely related, that took completely different evolutionary roads to get there. The elephant, with its crowd of guardian genes. The whales with their relentless repair and their 2-century lifespans. Other large, long-lived animals with their own quiet defenses. These lineages split from each other tens of millions of years ago. They didn't inherit one shared trick. They each ran into the same wall. Peto's paradox, the brutal math of size and time, and each one separately found a way over it. When the same solution appears over and over in unrelated animals, evolution is telling you something. It's telling you the problem had an answer, and that answer was reachable enough that life found it repeatedly. Cancer resistance at scale isn't a miracle that happened once. It's a door that's been opened many times by many different keys, and every one of those keys is still out there, written into the genome of a living animal, waiting to be read. That's the shift that turns this from a nature documentary into something that reaches toward us. Because if the problem is solvable, if the solutions already exist, already tested, already running in bodies swimming through the deep ocean right now, then they are, in principle, readable, understandable, maybe even, one day, useful. This is the quiet promise inside the whole story, and I want to be honest about exactly how far it goes, because this is precisely the kind of place where science gets oversold. Nobody is turning whale genes into a cancer cure. That's not the claim, and anyone who tells you otherwise is selling something. The real value is stranger and slower than a cure. It's the map. A sperm whale, a bowhead, an elephant. Each one is a body that has already run a multi-million-year experiment in cancer suppression and passed. The results of that experiment are sitting in their DNA. By studying how these animals hold trillions of cells in line for decades, we get to see which defenses evolution actually reached for when the stakes were survival. Not theories, solutions that already work in the harshest test there is. And notice the reversal buried in that. For our entire history, we've looked at these giants and been impressed by the obvious things, the size, the depth, the power of an animal that hunts in blackness under crushing pressure. We thought the marvel was on the outside. It isn't. The real marvel was always internal, cellular, invisible. It was the fact that this body kept itself from destroying itself quietly for a lifetime while we weren't even thinking to look. The whale we were watching was never the impressive part. The impressive part was happening inside every one of its cells, and we couldn't see it, which brings us all the way back to the title, and to the lie hidden inside it, a lie worth telling on purpose, because the truth it opens onto is better. Sperm whales do get cancer. That don't was never quite true. And I could have hidden that from you to make a cleaner story. But the honest version is the more disturbing one, and it's this. They can get cancer, they simply almost never do, at a rate so far below what their own biology demands that it exposes a crack in how we understood the disease itself. They don't get cancer is the myth. They should be drowning in it, and they're not, and we're only beginning to understand why. That's the real story. And the real story is stranger, because immunity would just be a fact. This is a mystery that's still open. Think about what that open mystery actually contains. Somewhere in the biology of these animals is a working answer to one of the things we fear most. Not a magic answer, a layered, costly, hard-won one. Better repair, harsher checkpoints, cells ordered to die at the first sign of danger, maybe just a slower and more careful pace of living. A balance struck on a knife's edge between resisting cancer and paying the price of that resistance. The whale didn't beat the disease for free. It beat it by building a body tuned so tightly against its own worst outcome that everything else had to bend around that priority. And it's been running that body successfully in the deep dark, dive after dive, for far longer than we've understood how. So here's where the whole thing lands, and it should change the way you see one of these animals forever. The next time you picture a sperm whale, that vast dark shape sinking into the black, thousands of feet down, into pressure that would crush anything not built for it, don't think about the size. Everyone thinks about the size. Think instead about what's happening inside that body on the way down. Trillions of cells, copying themselves in the cold, decade after decade, and a defense system running in every one of them, catching the mistakes, killing the dangerous ones, holding the whole animal together against odds that say, it should have failed long ago. We spent a long time believing cancer scaled with size, that the biggest bodies were the most doomed. The whale proves the opposite. Size didn't doom it. Size forced it to get better, to out-engineer a disease that quietly beats us, and to do it so well that we're still reverse engineering how. The old idea wasn't stupid. It was just looking at the wrong thing. It was watching the size of the animal, when the real story was written in the cell. And the strangest part is that the answer isn't hidden in a fossil or lost to some vanished world. It's alive. It's out there right now, in the deep, in an animal we've hunted and studied and thought we understood, carrying inside it a solution to a problem we're still fighting, and taking it back down into the dark every time it dives. We just have to learn how to read it before it disappears.